welcome again to this course on convex optimization. Today we are going to study theorems of the alternative. Now, theorems of the alternative are applications of separation theorem, and we have already studied separation theorems in the last lecture. Now, what is a theorem of the alternative? So, in theorem of the alternative there are two systems, system 1 and system 2. So, system 1 there is some equality or inequalities, system 2 there are some inequalities or equalities. So, what we say is that if system 1 has a solution, system 2 cannot have a solution, and if system 2 has a solution, then system 1 does not have a solution. Similarly, if system 1 does not have a solution, system 2 has a solution. If system 2 has a solution, system 1 does not have a solution, in the sense that if one of them can be solved, the other cannot be solved, both cannot be solved simultaneously. So, the goal is to show that system 1 and system 2 cannot be solved simultaneously. Now, why we are interested in such systems? That is the major question. This thing comes from the very notion of optimality. Now, let me consider a very simple problem: minimize f of x subject to certain constraints. Let us just take inequality constraints. Now, let me assume that this f and the g, each of the gi's are differentiable functions, and you already know the definition of differentiability. Now, let us consider a point f of x bar here. Let us consider a point x bar, and suppose we know, if we calculate f of x bar, and suppose this x bar is not a solution of the problem, that x bar is not solving it. Maybe let us look at the picture when we have no constraints. Then basically we are looking at the scenario where grad of f x bar is not equal to 0. So, I must now improve. So, I must move from x bar in such a way such that in such a direction I should move in this direction d, such that if I come to a new point, say x bar plus some lambda times d, f of x bar plus lambda times d should be strictly less than f of x bar, and you should be able to find such a lambda. That is exactly what is done in the unconstrained optimization algorithms. This is exactly what you have to do: find a lambda, find a d. D is the direction of descent. So, if you move along the direction d, and if you move within the scale limit of lambda, then your function value actually decreases. You go to a value which is lesser than your current functional value, and you check whether the minimum is attained at this point or not, or at least if this is satisfied, and then move down again. So, this procedure, how do I get such a d? I mean, how will I guarantee such a d? Observe that if I have this condition true, if I can find a d such that this is true, then by definition I can write this as f of x bar plus lambda d minus f of x bar, just writing down the Taylor's theorem, nothing else. You can figure this out very soon easily. This thing is strictly less than 0, where lambda is running down arrow to 0, and you must observe that once I know this by the very definition of a limit, I can show that there would exist lambda bar such that for all lambda between 0 and lambda bar with both of these not included, we have f of x bar plus lambda d minus f of x bar by lambda is strictly less than 0. So, this would imply that f of x bar plus lambda d minus f of x bar to be strictly less than 0, because lambda is positive. This would imply that f of x bar plus lambda d is strictly less than f x bar, a thing that we exactly wanted. So, any d which satisfies this relationship, this sort of d is called a direction of descent. Now, if I am now considering this problem where I have constraints, then what I can show is the following, that if I consider this system, sorry, I made a mistake. This system has no solution in D, that is, there is no D which satisfies the above system if x bar is a local minima. So, there is no such D which will solve this. You see, you can figure out this quite well, and I would ask you to figure out this as a homework, that if x bar is a local minima to this problem which we can call as P, then this system has no solution if x bar is a local minima to P. Now, the question is, if this is not solvable, is there something else which is solvable? Is there some other system which is solvable? So, it will allow us to characterize the necessary condition for a local minima, which is fundamental, because that characterization would allow us to compute a local minima. This is exactly or precisely the point where the theorem of alternative arises. So, this is the place where theorem of alternatives entered the picture. Look, what is this system telling? This system telling that this is a linear inequality, this is a linear function, and this is an affine function, right, in D. Now, this system of linear and affine functions with strict inequalities, they do not have a solution, which means that in general I am looking at this system, that okay, I have a system of say convex inequalities. I am just generalizing this because these are all subclass of convex functions. So, if I have m convex inequalities and I am saying okay, this system has no solution. So, what is the certificate? Means how do I say that this system has a no, this system does not have a solution? If this system does not have a solution, something else has have a solution. That okay, if something is solvable, I can say that this system does not have a solution. That is that particular something is called the certificate of solvability or unsolvability of this system, and this is precisely what optimality is all about. This is exactly optimality of the point x bar, local optimality. So, we have generalized this thing into this framework. We will show how this will be applied. Now, this leads to our first optimality theorem, or sorry, first theorem of the alternative, which is called the Gordon's theorem of the alternative. Now, I have two systems, system 1, system 2. Let us see, let us write down the two systems. System 1 is exactly what we were just discussing, that you have a chain of m inequalities with convex functions. These are all convex functions, m convex functions, and we are looking for an x in Rn which will satisfy all this, or else the system 2 says that there exists, that I am trying to find a lambda in Rm plus, that is all the components of this vector in Rm is non-negative, and lambda is not the 0 vector in Rm, such that when individual components of lambda are multiplied with these Fi's, and this sum is always greater than equal to 0 for all x you want take. You could actually remove this Rn by some convex, closed convex subset of Rn. So, that will also work. So, now if I want to prove this, what I want to show is that whenever system 1 is solvable, system 2 is not, and vice versa. In the system, both of them cannot be solved simultaneously. So, both the theorem's conclusion is that both of them this is the conclusion. Now, if I prove, for example, if system 2 has a solution, it should imply system 1 has no solution. So, this is a statement P implies Q. So, then this fact is equivalent to this, it is same, this is equivalent to this, that system 1 has a solution implies system 2 has no solution. So, if I prove this, the second thing, I have actually proved both of them. So, let me just show you that okay, if I take system 1 as a solution, so if I am assuming this part, so if this is assumed, so this would imply that there exists an x in Rn for which each of these inequalities hold. Now, I have to show that system 2 has no solution. So, on the contrary, assume that system 1, sorry, on the contrary, assume that system 2 has a solution. So, I have to prove that it has no solution. So, I am taking the contraindication, I am taking the opposite assumption and then proving that there will be a contradiction. Assume that a system 2 has a solution. So, means there exists a lambda in Rm plus, but is not the 0 vector such that lambda 1 f 1 y plus lambda m f m y is bigger than equal to 0 for all y in Rm. Now, so hence in particular for the given x, in particular lambda 1 f 1 x plus lambda m f m x is greater than equal to 0, because x is one of these elements. Now, where x is again a solution of this system. Now, I know for this particular x f 1 x is strictly less than 0, f m x, f 2 x is strictly less than 0 and dot 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 f m x is strictly less than 0. Now, all these lambda 1, lambda 2 dot 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 lambda m are greater than equal to 0 and one of them at least is non-zero, which means that there is at least one element where lambda, say lambda k is strictly bigger than 0 and f 1 x is strictly less than 0, f k x is strictly less than 0 anyway. So, f k x is anyway strictly less than 0. So, there will be at least one k for which lambda k f k x would be strictly less than 0. So, on a whole, since x solves system 1, because this happens, it implies that lambda 1 f 1 x, this finally must be strictly less than 0. So, which means now we have a contradiction. So, this is the, thus we have a contradiction. So, we have proved two things. We have proved system 1 has a solution, system 2 has no solution. So, once we have, so because we have a contradiction, so our assumption that the system 2 has a solution is wrong. So, whenever system 1 has a solution, system 2 does not have a solution. So, simultaneously we have proved that if system 2 has a solution, system 1 has no solution. Now, we will go for the remaining one. I will say okay, if system 1 has no solution, see look what I have done here, maybe I am just crossed a page. What I have done here, I have said that system 2 has a solution implies system 1 has no solution, system 1 has a solution implies system 2 has no solution, but I have not said if system 1 has no solution what would happen, right. So, here I am trying to prove that okay, if system 1 has no solution, then it should imply that system 2 has a solution. This would say that if system 2 has no solution, this is same, this system, this is equivalent, because if a statement P implies a statement Q, the negative of the statement Q implies the negative of the statement P. System 2 has no solution implies system 1 has a solution. Now, if this is what I have to prove, so I just have to prove any one of them, I will prove the first one. So, let me assume that system 1 has no solution. Now, let me write down a set, let me construct the set A which is of the form there exists x in Rn such that y can be written as f of x. I will write tell you what is f of x as the interior of Rm plus, that this f of x is a vector consisting of these real numbers f1x, f2x, fmx, because these functions are all convex functions from Rn to R, which is so obvious that I am not repeating this fact, but here I have written everything into form of a vector. So, what I am doing, I am taking an x and computing this and adding to it some element from the interior of Rm plus, that is I am adding to it another vector whose all components are negative, whose all components are positive. So, here I have a fx, I am taking a x in Rn. So, how is my y constructed? I am taking an x in Rn, computing this fx, that is making this vector, and then with it I am adding a vector whose all components are positive. In effect, A can be written as f of Rn plus int of Rm plus. This is the way A can be written. Now, if you look at it carefully, so this is in Rn and this is in Rm. So, A is a subset of the Cartesian product of Rm cross Rn, that is it is in the space Rm plus n. Now, what I need to do here is to tell you that this set is a convex set. So, your homework is prove A to be convex. So, this is your homework, do not mind it. So, exactly the convexity of the function is needed to prove that this set A is convex. So, once you prove this, you have to observe another fact that A is a open convex set. So, A is an open convex set, it is not a closed convex set, because we are talking about the interior of Rm plus. So, basically if you take this interior Rm plus, you construct a set like this fx plus interior of Rm plus, then basically you have translated an open set, you have made this as the origin. So, then this would remain to be an open set. So, why? So, these sort of sets whose union is actually, or you can write it like this, union of fx plus int Rm plus x element of Rn, this is your set A. Now, these are open sets. So, arbitrary union of open sets is again open. So, this is an open convex set, and 0 is not an element of A, because if 0 is an element of A, then there would exist x hat in Rn and W element of interior of Rm plus such that 0 is equal to f of x hat plus W, or f of x hat is equal to minus W. Now, every component of minus W is strictly negative. So, every component f1x, f2x, fm, this all of these. So, this would immediately imply that f1 x hat is strictly less than 0, to fm x hat is strictly less than 0, which shows that x hat is a solution to the system 1, but I have said that x1, the system 1 has no solution. So, it means that this conclusion is correct, that 0 cannot be an element of A. Now, I ask you to apply the separation theorem. You might ask me a question now. You are asking me to apply the separation theorem, but how can I do so? Because you have just told me that okay, you take a closed set and a point outside it, you can strictly separate it. But here you are telling that the set is open and then you have a point outside it and you are asking me to apply the separation theorem. The problem is this, that okay, maybe the set convex set is open, that like I have a convex set like this, a set C which is open, that is I do not have the boundary. Now I have a point just on the boundary, then also this point say x is actually outside C, it is not in C. So I can actually, I will not have a strict separation, but I can have a hyperplane passing through this point. So I will have a separation. So if x is not in some set C and C is open, there exists a P not equal to 0 such that P of x is always bigger than P of y for all y in C, or P of y is always bigger than P of x for all y. It could have be the reverse equation also, you could change the inequality, it does not matter. So here we have A to be an open set and 0 is outside A. Now here actually 0 means 0 0, basically this is the 0 of Rn and this is the 0 of Rn. Now if that is so, then how do I go about applying the separation theorem? So we will just have to look into this thing. So there would exist some lambda mu not equal to 0 and lambda mu is element of, I am applying the standard thing Rm cross Rn such that lambda mu times yz is bigger than equal to lambda mu times 0 0 for all yz in A, or xz. What did I show? Sorry, I think I just have to go back and look into this thing, all xy. For every xy that you have, there is a mistake, there is a mistake in the set construction. So we will first prove that system 1 has no solution, and let us construct this set A which is given in this way, that it consists of all y in Rm for which there would be an x such that y can be written as fx plus some element from the interior of Rm plus, that is this vector would have all its components strictly greater than 0, and this f of x is actually a vectorial representation of the system of functions we have f1x dot dot fmx. Now A can also be written in this form, which is same as writing this. If you this set interior of Rm plus is an open set, and when you translate it by fx, this remains an open set. So for each of these x, this is an open set, and when you take a union, this would also be an open set, and A is an element of Rm, is a subset of Rm. So you have to prove that A is a convex set, which is of course an open convex set, because we have proved the openness. A is a convex set, which is your homework, and that is observed by observing that each of these f1, f2, fm are convex, and 0 is not an element of A, because if 0 is element of A, then you see there would be an x hat and a w for which this would be true, and then I can take w to the other side, and now each of the components of minus w is negative, showing that this is negative and that is x hat is a solution of system 1, which is false because system 1 is assumed to have no solution. Now we have to apply the separation theorem. Now you might ask me that okay, in the previous separation theorem story we had talked about a closed set and a point outside it, and you can have a strict separation, but when you have an open set like this, if you consider this convex set, when you have everything inside, but you do not have the boundary, then any point on the boundary can also be a point which is not contained in C, but through such a point also you can draw a hyperplane containing x, which puts x on the hyperplane and the whole set C on the other part of the hyperplane. You see that the open set C is actually strictly inside the hyperplane. So, what you can say is that this result will always hold true, irrespective of whether your set is open or closed. So, this sort of separation, the standard separation, will always hold true. Of course, this inequality can be reversed also, it is up to you. So, now here we do not have 0 in A. So, then applying separation theorem, there exists lambda element of Rm and lambda not equal to 0 such that lambda of y is greater than equal to lambda of 0 for all y in A. This is a standard separation theorem. I have just reversed the inequality, it does not matter. So, lambda of y is greater than equal to 0. Now, how does a y look like? So, there exists an x. So, take a y. So, there exists an x such that y is equal to f x plus some q, where q is element of interior of R m plus. Now, you take any element in the interior of R m plus, say q, and you construct the element epsilon q, where epsilon is greater than 0. Right. This is what you can do. So, then this epsilon q will also have all its components to be positive. So, this will be also in interior of R m plus. So, if I construct this element f of x, this x plus epsilon q, then this is also in the set A. So, now I can put this here to show that lambda times f of x plus epsilon q is greater than equal to 0, right. Now, if epsilon goes to 0, it immediately shows that lambda times f x, because in the limit this is what is going to happen. Now, this x was arbitrary, you could choose any x and construct elements like this. So, you could choose of one x and construct an element and prove that for that particular x this will be true. You could do another x and do the same thing. So, this is true for every x. Now, take r to be greater than equal to 0, and 1 by r is greater than equal to 0. So, 1 by r into q is element of interior of R m plus if q is in the interior of R m plus. Actually, you know, interior of R m plus is a cone, and so it is a conic structure. So, this is obvious, because if you take a positive number and multiply by a positive number, this is a positive number. Now, construct this element, take an x bar, fix a x bar, fix x bar, and construct the element f of x bar plus 1 by r times q. Now, this q could change, take any q. I have taken a q, constructed this 1 by r, fixed up the x and constructed this element, and this element is again in A. So, again by the separation theorems, lambda of f of x bar plus 1 by r times q is greater than equal to 0. So, it means lambda times R f x bar plus lambda times q, this is just inner product, we have multiplied by R, and so is greater than equal to 0. Now, as R goes to 0, this will go to 0 because it is a fixed number. So, this will go to 0 and the inner product that will go to 0. This will imply lambda q is greater than equal to 0 for q element of interior of R m plus. Now, this q is arbitrary. So, this is true for all q in the interior of R m plus. Now, take any q naught or take any such p in R m plus. Now, because R m plus is closed, any such p is an limit point. So, for every element in the interior you have proved this is true. Now, take p in R m plus and just take p to be in the boundary of R m plus. So, there exists a sequence q n with q n in the interior of R m plus such that q n converges to p. Then what I have is again that lambda of q n is greater than equal to 0. So, this would immediately show as n tends to infinity, lambda of p is greater than equal to 0, but this p was an arbitrary element. So, what I have shown at the end is lambda times z is greater than equal to 0 for all z in R m plus. So, this is true. First I have proved that this is true for all p in the boundary of R m plus, and we have showed that everything is true. This is true for all q in the interior of R m plus. So, it is true for every z in R m plus, and hence lambda must also be an element of R m plus, which is obvious because it is for every non-negative vector it is giving you greater than 0. So, it must, so it is making an acute angle. So, it must itself be in R m plus. So, that is exactly what we have proved. We have proved that lambda is in R m plus, and also we have proved that lambda of f x is greater than equal to 0 for all x in R n. So, what we have showed that system 1 has no solution would imply system 2 having a solution. So, we have proved this part, and hence we have also proved this part. So, let us see how do we apply this result. So, here we will apply it to the optimality condition to find the optimality condition for a local minima and get a result, which we will soon discuss. So, Gordon's alternative theorem is not the only alternative theorem. There are many alternative theorems like Mochkin alternative theorem, Tucker's alternative theorem. There is also an alternative lemma or alternative theorem due to Farkas called the Farkas alternative theorem. So, all these are very well represented in the book by Mangasarian. So, Mangasarian is the author. He wrote a book in 1969 titled Nonlinear Programming, and it has all these beautiful results. But you see, let me tell you, all those results are given in terms of matrices, that is, instead of convex functions that we have used in the Gordon's theorem, they have used linear functions. Does not matter because a lot of these things are only for linear function, and it is not so easy to put them into the convex framework, and here we have put it into the convex framework to make it more general. Another book is titled Foundations So, this book is no longer available from its original publisher, it is now available through SIAM in their Classics in Applied Mathematics series. Foundations of Optimization. This book also has a fabulous discussion of theorems of alternative by Osman Guler. This has just come out from Springer in 2011. It is a lovely book with very good discussion on optimality conditions and theorems of the alternative. So, let us go ahead and do this application. So, as an application of the Gordon's alternative theorem that we have just learned, we would go back and try to apply it to find the necessary optimality condition for the problem P that we started in the very beginning. That okay, if this is a differentiable optimization problem with inequality constants, what is my optimality condition? What is my necessary condition for optimality? That given if x bar is a local minima, can I tell what sort of conditions it will satisfy in terms of the gradients of this function? And that is exactly what we are trying to now prove or rather find using the theorem of the alternative. Now, as we have already discussed that our major impetus of studying these theorems of the alternative is to look into this fact that this is exactly what happens if x bar is a local minimum of P, that this system has no solution in D. Now, if this system has no solution in D, if you observe this function is linear in D and this function is affine in D. So, all of these are convex functions. So, now this corresponds to the first system 1 of the Gordon's theorem of the alternative, and what we are telling essentially is that optimality of x bar or local optimality of x bar is same as the first system of the Gordon's alternative theorem, and that system has no solution. So, the second system would have a solution. So, it means that there would exist scalars, that is each of them there corresponds a scalar. So, like you have scalars corresponding to each f I, lambda is a scalar corresponding to each f I. Here also you have scalars corresponding to each of these functions. So, there will be a scalar corresponding to this, which is lambda 0, corresponding to g 1 x bar g 1 grad g 1 x bar d lambda 1 dot lambda m. All of this has to be greater than or equal to 0 by Gordon's alternative theorem, and the full vector cannot be 0, it has to be a non-zero vector, and you keep on multiplying with this, and this is exactly what you will get. This is true for every d, this has to be greater than or equal to 0. So, because it is true for every d in Rn, I consider in particular d is equal to 0. That would immediately leave me just with the equation, because if I put d equal to 0, this will go and this will go, it would just leave me with the inequality this is greater than or equal to 0. Now, what does this mean? Observe that I have said that x bar is a local minimum to the original problem. So, which means this x bar is feasible to the original optimization problem, which means x bar is a solution, means it has to satisfy the constraints. So, all of this g I x bar is less than or equal to 0. Since x bar is a local minima, it would imply that g I x bar is less than or equal to 0 for all I equal to 1 to m. Now, since lambda I is greater than or equal to 0 for all I equal to 1 to m, it would immediately imply that the summation lambda I g I x bar, this must be less than or equal to 0, because you are multiplying negative and positive quantity and then you are adding all negative, non-negative, non-positive or negative quantities. So, that is less than or equal to 0. But then this would contradict with this. So, if both of them has to be satisfied, the only way is to have this. So, this would imply Now, because each of them are negative quantities and all of them add up to 0, which would imply that all of them has to be individually equal to 0. Now, so once this I know to be is to be 0, so what I am left with is lambda naught grad f x naught f x bar d plus summation lambda I grad g I x bar d is greater than equal to 0 for all d. So, this can be simply summed up and nicely written as lambda naught grad of x bar plus summation I equal to 1 to m Now, this is true for every d. So, if I put this vector as w, then I am saying that w d is greater than w inner product d is greater than equal to 0 for all d. So, if I put instead of w, if I put minus w in d as minus w, so it will show me that the norm of w square would be less than equal to 0 and hence w would be 0. So, if this happens for all d, it essentially says that a linear function cannot always contain, for every value of the variable it cannot be non-negative, it has to be both negative and positive in that sense. So, this would imply immediately that lambda naught So, combining this and the fact that all these values lambda naught dot 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 lambda 1 all these are not equal to 0 simultaneously leads to the famous John optimality conditions or Fritz-John. Fritz-John is the full name of the person, the title is John. I do not know why they always use Fritz-John. So, you could have written like this also. This comes to the John optimality conditions given in 1948. By the way, when he first sent this result, which is very crucial because he has used optimality conditions for inequality constraints, till that time it was optimality conditions with equality constraints which were important and they were solved by the Lagrange multiplier technique. But modern optimization and modern applications, inequalities are the hallmark of the constraint representation. So, thus John's optimality condition was the first to handle inequalities and thus it is very important. But the interesting fact is that when he first sent this paper to the Duke Journal of Mathematics, it was rejected and was published in a conference. In fact, many good mathematical papers were only published in as conference proceedings. So, this shows that if x bar is a local optima, local minimum I would say, because I have already said it is a minimization problem. So, local minimum of P, then there exists scalars is real numbers basically lambda naught greater than equal to 0, lambda 1 greater than equal to 0, lambda m greater than equal to 0 means whatever we had written earlier, such that all are not simultaneously 0, that is lambda naught, lambda 1, lambda m all are not 0, all are not simultaneously 0. Such that number 1 lambda naught times The second condition is very important, it is called the complementary slackness condition. It says that both of these lambda I and G I cannot hold with strict inequality at the same time, that is lambda I strictly greater than 0 and G I x bar strictly less than 0 cannot hold, because then this product would be strictly less than 0. So, if G I x bar is strictly less than 0, lambda I would be 0. So, but if G I x bar is equal to 0, lambda I can be equal to 0. So, all these constraints where G I x bar is strictly less than 0 are called inactive constraints, because lambda I is equal to 0. So, we end our talk today with the deduction of the famous John optimality condition, and you see how in this case where f and Gi's in this case are not been assumed to be convex, just they have been assumed to be non just differentiable, we have been able to use convex tools to prove the optimality condition, thereby showing the power of convexity itself. Thank you very much.